Hey everyone, this is the second of two parts of our gas lecture content, and I'm using an old PowerPoint for this. I will link this entire PowerPoint in the lesson. However, I'm starting partway through it, so you'll have to scroll down if you want to see this. Something I wanted to point out, and it's sort of just something that exists at one particular temperature and pressure combination. Um, Now, STP, right, stands for standard temperature and pressure, and it is almost exclusively associated with gas chemistry. And standard temperature and pressure, abbreviated STP, is 0 degrees Celsius, right, which is, 273 Kelvin and 1 atmospheric pressure. And so if a problem does refer to STP, you know that that refers to this specific temperature pressure combination. Now, I don't want you to confuse this with standard conditions, which is another common temperature pressure common combo that is often used. And the term standard conditions means 1 atmosphere pressure, but 25 degrees Celsius or 298 K. So even though they sound similar, standard pressure and temperature, STP, and standard conditions, they actually refer to two separate things. And you should know the difference between them. So standard conditions is a little bit warmer than most people's room temperature, and the room temperature tends to be around 21, 22 degrees Celsius, somewhere 20, 21, 22. And standard conditions is at 25 degrees Celsius. So whenever we see our labels for example, enthalpy or entropy, right? That's superscript with the 0 means standard conditions at 25 degrees Celsius and 1 atm. And for gases, STP, it's at 0 degrees Celsius. And so, but when you see that superscript, it specifically refers to this. So the 25 degrees Celsius. All right, moving forward. We're going to pick up in the middle of section 5.4 in your textbook, and I'm referring to what's called Dalton's law of partial pressures. Now, Dalton's law of partial pressures is really quite intuitive, and tenet one is that if you have two separate gases, in this particular picture here represented by red and green dots, that whether you're going to combine the gases, as this diagram shows, or whether you're just looking at one container containing both of those gases, the total pressure inside the container is equal to the partial pressure of each particular gas added up. That's what this is referring to. These are called partial pressures, and it refers to the pressure due to just one of at least two, but it could be more, two or more gases in the sample. Okay? Now, I know that sounds, and it is pretty intuitive. But here's where it gets a little bit more complex, but not really. And so one thing that you could do is if you were doing a Pivnert equation, for example, you could do it one of two ways if you're referring to an individual component of the whole. So you could look at Pivnert and calculate each of the gases independently. So for what I mean by that is if you knew the moles of just gas A and you knew the moles of just gas, or you know the moles of A and you know the moles of B in a particular container, and you know the temperature of the container, you know the volume of the container. So actually they're the same for both of these, right? T and V are going to be the same. You can calculate the partial pressure of each gas by only plugging in that gas's moles into Pivnert. And you would get, right, A and B individually for their pressures. Now, you could add them up, right, to get the total pressure inside the container. Now, the other way you could do this is to calculate what's called the mole fraction of each. So that's what x refers to here, even though it looks like a fraction, doesn't it? So what it means is it's the part over the whole. So basically, it's the decimal of that moles of the individual gas. So for example, if you had 4 of A and you had 6 of B in a container, the partial pressure of the gas A could be figured out in a couple of different ways. You could plug A into Pivnert, or what you could do is if you were told, let's say the total was 10 atmospheres, okay? Now, the partial pressure of A is A's moles, 4 over 10, and it's usually not expressed as a fraction, but instead as a decimal, right? 0.4. So even though you set it up as a fraction, you typically express it as a decimal. And the reason is because you can't show sig figs with a fraction. And we all know what happens when sig figs are forgotten about. And then the mole fraction of B is 6 over 10, right? 0.6. Now, if you have the total pressure, you could actually just multiply the you can multiply the mole fraction of A times 10 to get the partial pressure of A. You could multiply the mole fraction of B, which is 0.6 times 10 to get the partial pressure of B. And that's what this is telling you here, right? The partial pressure of any component is equal to the mole fraction of that component times the total pressure. So this here individually is what I was talking about over here on the right. So knowing how to calculate the mole fraction is simply, you've done it all your life in math class, and you've done it even in this class. It's just now given a formal name. It's almost like calculating like the percentage, right? You take the part over the whole, but you're not multiplying by 100. You're just leaving it as the decimal, okay? So an example is a sample of natural gas contains 8.24 moles of methane, 0.421 moles of C2H6, right? So that's going to have no double bonds, so that's ethane, and 0.116 moles of C3H8 propane. If the total pressure of the gases is 1.37 atmospheres, what is the partial pressure of just propane? So we figure out the mole fraction of propane by taking the moles of propane, right, the 0.116. So we're just taking the part that we are interested in, and we're dividing it by the whole. And in this case, the whole, right, is all of these moles added up, 8.24, 0.421, and 0.116. And the reason why we output as a decimal, right, is we're able to maintain the 3 sig figs in all of the measurements above. Leaving it as a fraction kind of leaves it with an indefinite number of sig figs. So now that you have the mole fraction of propane, you simply multiply this as a decimal, right? Not as a percent, as a decimal, we leave it like this, times the total to give you the partial pressure of just the propane. Now, of course, if you really wanted to be thorough, you could go on and answer the question, like, what is the partial pressure of methane and the partial pressure of ethane? And they should all add up to our total pressure. And if they don't, you have made a mistake, right? That's a way of double checking. Now, something that we also would have done in the lab, ooh, geez, I wish, it really kills me to be at home not doing things with you guys. Because, science is very much about, right, experiment. We look here at a gas trap. Well, if you're going to produce gas and you want to trap that gas, well, you can't let it escape into the atmosphere. And so, one way in which you can determine how much gas is produced is by using a setup like this. So here's the chemical reaction, right? One of the reasons why potassium chlorate is particularly dangerous is because when you heat it, it produces oxygen. and that oxygen can feed a fire. So when we made smoke bombs, we used potassium chlorate to provide an excess source of uh, oxygen, causing it to really flame up. Also, potassium burns kind of like a violet purple color, and that's why if you were looking closely, sometimes you can see the purple color that's burning when we made our smoke bombs. But anyway, so instead of allowing the gas to go into the atmosphere, what we're doing is we're trapping it. And so this gas is bubbling out, right? This is oxygen gas. It is bubbling out and it's being trapped in this container. Now, I don't believe in 10th grade we really accounted for this, but the reality is you don't actually have pure oxygen gas in there. Oh, and by the way, the potassium permanganate is just going to be a catalyst. Now, the reason why this particular reaction doesn't, well, it produces pure oxygen gas, but you're not actually collecting pure oxygen gas. And the reason is because anytime you do something like this, right, you're collecting gas over water. And so some of the liquid water will invariably have evaporated off. And so you actually don't just have pure oxygen gas. Whenever you bubble anything like this through water, you also have some water vapor above it, some H2O gas. And so along with the oxygen trapped, right, you don't just have O2, but we also have some CO2, both of which, or I'm sorry, H2O, both of which are gases floating around in this bottle. So if you were to do a Pivnert calculation, right, and if you were to, let's say, if you knew the liters, right, of this gas, we knew the temperature, right, at which it was collected, and this is not going to generate excess pressure or less than room pressure, right? And so if we bubble this up, and you can actually raise this bottle up and down, right? And you can actually determine, you know, if you raise it to where the water level is right here and you have no height difference, there is no additional calculation to actually do, right? So when the bottle just fills, the height, that delta H, right, when we look at at the manometer kind of setup, doesn't exist. And so the pressure inside the room is equal to the pressure inside the bottle when there is no water height differential. When you have the gas that is bubbled out just at the surface of where the water is. Now, also, the other thing to note is that because water is much less dense than mercury, um, even differences this big are actually minuscule because mercury has a much denser liquid than water is, and so therefore the two heights are not equivalent. And so um, water has a much larger spread than mercury does. That said, um, how exactly then, if I have the air pressure, the temperature, and the liters, would you figure out how many moles of gas in there? That's right, you could use Pivnert, right? PV equals nRT. So you could solve for M. Now, the problem, of course, is that the pressure inside is due to two gases, not just one gas. So if the pressure in the atmosphere is something you can read on the barometer in a classroom, and if it said, let's say 0.830 atmospheres, you can't just take that as the pressure due to the nitrogen. It's actually the pressure due to the nitrogen plus the oxygen. And so, as this equation down here tells us, right, since they're both in there. So what you do is you look at a handy dandy chart. And what you see on this chart is if I measure the room temperature, right, if it's a warm room and it's at 25 degrees Celsius, this is the 23.76, the millimeters of mercury that I need to subtract from my total pressure to give me the pressure that's just the oxygen, right? So I would have to convert my ATMs to millimeters of mercury, and then, so that would be the P total, okay? Because I'm using the room pressure and assuming the pressure is inside and outside the same. So if I have my 0.830, I subtract out, right? I convert that to millimeters of mercury, and then I subtract 23.76, right, which is this, isolating this, right? When I move this over to the other side, it becomes a negative. Something else you'll notice, which shouldn't be a surprise, is the warmer it is, right, the more gaseous or H2O you're going to get. So the warmer it is, the higher what's called the vapor pressure, the pressure exerted by the water gas above that body of water gets higher. It's also known as the partial pressure of water. Okay, you'll have a practice problem inside your textbook to work on to see if you really fully understand that concept. All right, kinetic molecular theory of gases. So um, the kinetic molecular theory of gases describes gas behavior. And what it does is it describes ideal gas behavior. And if you were to be asked, what is an ideal gas? An ideal gas follows or has these sort of characteristics. So, a gas is composed of molecules that are separated from each other by distances far greater than their own dimensions. That is true. The molecules can be considered to be points. That is, they possess mass but have negligible volume. Most of the time, that's also true. Essentially, they're these volumeless points. Now, obviously, there may be certain conditions in which that is less true than other conditions. For example, if you have a very tiny container versus a very large container. A very large container, this sort of statement is more true than if you have a small container. Or if the gases themselves are very large versus tiny little helium atoms. Point number 2, gas molecules are in constant motion in random directions. Collisions among molecules are perfectly elastic. So, and what's also often stated in addition to this is they move in straight lines in random directions. And then they hit something, whether it's another molecule or the sides of a container, and then they bounce off without losing any energy, right? That's what perfectly elastic means. Now, of course, that is not necessarily true, right? We also know that energy is lost during collisions due to friction and other, sound sometimes. So we don't have perfectly elastic collisions. And also, the assumption that gases move in straight lines and in random directions is pretty true. They move in a straight line until they hit something, and that is quite true. Number 3, gas molecules exert neither attractive nor repulsive forces. Of course, gases can be charged and they can be polar. And so the more polar or charged they are, the less true point number 3 is. And the average kinetic energy of molecules is proportional to the temperature of the gas in kelvins. Any two gases at the same temperature will have the same average kinetic energy, and that is also true. So the 2 points that I think are going to be questioned the most, right, by some gases is point number 1 and point number 3. That said, an ideal gas, right, follows this sort of kinetic molecular theory without any deviation. And the ideal gas law predicts what the pressure might be under certain conditions of a gas, right? The moles, the volume, the temperature. And if a gas is ideal, what it means mathematically is that the Pivnert equation gives you the exact right answer every time. Theoretically, that matches experiment. So for gases like a helium, right? Heliums are tiny, they are nonpolar, and so you would expect helium to behave very much like an ideal gas. It should have very little attractive forces to other heliums, and when you put it in a container, because it is itself tiny, the container size will have less of a sort of cause for deviation in point number 1. So being an ideal gas, right? Helium is probably the most ideal gas. Possibly H2 also is a very ideal gas, right? It'll also be nonpolar. Now, what this means is when you do Pivnert, okay, these two being very ideal gases, in theory, The value, let's say I'm calculating pressure, right? I have a container of a certain volume. I know what moles I put in there. R is constant, and I know what temperature it is. I'm going to get some value for that pressure inside that container. And the pressure, the theoretical pressure that I get out of PIV-NERT from this equation matches experiment, matches reality extremely well if it's an ideal gas. Now let's take a look at the fact that some gases are less ideal than others. Now, when I look at this, I see that if the blue line represents a 1, meaning if I have a certain pressure, a certain volume, a certain, well, R's are, and a certain temperature, right? Maybe PIV-NERT predicts that I should have, well, PIV-NERT predicts I should have this many moles of N, and that answer is 1. Now, for an ideal gas, what that means is ideal gases give me exactly what PIV-NERT says it should be. However, you'll see all these different lines, right? Different gases deviate from ideal behavior, some more than others, right? Now, when it comes to deviating from ideal gases, we're going to look at concepts like polarity, and we're going to look at concepts like volume and size. So when I look at this, all right, let's say right here, I'm looking at this gas. Now, effect of intermolecular forces on the pressure exerted by a gas. The green balls could either be more of the same element as these red balls, or they could be a different gas, and you could have two gases in the mixture. So it could be a sample of pure gas or a sample of two or more gases together. The point is that think about what would happen. As this gas is moving toward the wall, right? It's going to hit the wall and ricochet off. This is the source of pressure, right? This hitting the wall and then ricocheting off. If this gas is attracted to other gases in the sample, whether it's to more of itself or a different gas, that could slow down, right? The speed with which it collides against the wall. So these attractions, right, could potentially slow down this little red ball, bam, and it won't hit the wall with as much force. So you can see how polar gases might cause deviation from ideal behavior because what they're going to do is actually affect the the velocity of the gases themselves due to these attractions. So here is what's called the van der Waals equation. And so even though it looks a little complex, really what it does is it looks like PIV-NERT, right? This is P, this is V, this is nRT, except P and V have what are called correction factors. There is A and B. So notice that A inside these parentheses, right? A is something that corrects P, the pressure. So if it's not an ideal gas, what's going to happen is that the experimental pressure or the pressure in reality is not going to match the pressure P that you get out of PIV-NERT if you do a calculation. This corrects the calculation. So the A factor corrects for polarity for the reason we discussed above. If gases attract one another, they're not going to hit the sides of the wall of the container with as much force, and they're going to decrease the pressure. This A factor, with the plus right there, brings the pressure back up in the calculation so that it ends up matching the actual output, so that the P that outputs from there is sort of is going to match the P in experiment. Notice that N and V are also part of that. And so N is the number of moles and V is the volume of the gas. And so, I'm sorry, V is the volume of the container. And so it's just, you don't ever have to do this calculation. You just have to explain perhaps why A is there or what type of gas would have a higher A value. So the more moles of gas, the more the pressure needs to be corrected, and the smaller the container size, the more the pressure needs to be corrected. And so that's what the N and the V are also part of that A. Now, with the A, the higher the polarity of the gas, the larger the correction factor. So ammonia is a polar molecule, right? Ammonia should have a higher A factor than something like helium, okay? Because helium is a nonpolar gas. The B factor corrects for gas volume, okay? So what if I'm comparing methane, CH4, which is a nonpolar gas, to something like C3H3 propane, which is another nonpolar gas? You can see how methane would be smaller than a propane molecule. So with the same number of moles in the container, if I have 1 mole of this and 1 mole of this, right? Which one takes up more container space? Obviously the propane. So therefore, larger gases need more of a correction for the volume. So you never have to memorize what these values would be. You simply would have to look at a table or argue for them. For example, argue for them sort of theoretically why that is true, right? So krypton, which is a large, right, noble gas, um, xenon, which is a large noble gas, both of those have larger A factors than like helium or neon, right? Those are smaller noble gases. And that's because these are more polarized, even though they're nonpolar, they're more polarizable gases. And so therefore they have large volumes and more polarizable, and they also have generally larger. Um, well, that's interesting. Why the B value here is kind of larger for helium. That's interesting. But generally, you would expect these values to go up. I'm pretty sure that this might be a typo. This isn't mine. This is a purchased PowerPoint. And so you can see how, certain types of gases would have larger A factors than others. And so if something follows a trend, then you would explain it by, well, the more polar gas has a larger A value. But something may not follow an expected trend. And you may wonder why, for example, why would water have less of A factor, that corrects for pressure than something like a um, CCl4, which is also so this is polar, but this is nonpolar. And CCl4 has this giant A value. Well, I would guess that the CCl4, because even though it's nonpolar, because it's a perfect tetrahedron, even though the individual bonds are polar, right? But the tetrahedral geometry cancels that out and it's a nonpolar molecule, it must be incredibly polarizable rather than the small water. So that's how I would actually, describe that. And actually, when you look at the volume correction too, the volume correction is much bigger than that of water, which is definitely expected. So this trend in A bucks what I would consider a normal trend, and B, it follows the normal trend, right? So I would attempt to explain this through polarizability and say that even though CCl4 is nonpolar, because of its perfect tetrahedral geometry, it is extremely polarizable, making its A factor larger than water. Now, again, you don't have to memorize this table. You would simply put things generally in an order of nonpolar and small generally has a low A value, and polar or even charged, right, has a large A. And then with volume, it just tracks with molar mass. All right, a couple more points to be made in this lecture. I want to go back up here. All right, so what we find is that this machine here, this is an oven. It heats up atoms to the point where they become gaseous. They come flying out. This is a collimator, which just sort of like This is a collimator, which kind of makes it into a beam. And then this is a disk that's rotating. And generally, because of how many dots appear over here as it rotates, what you can get is a distribution. And you can determine, like, generally how fast or how slow um, gases are moving within a certain distribution set. And so one of the things we find here is that there isn't just one velocity. So we know that as temperature goes up, velocity goes up, right? With our gases. But what we don't know is that there is an actual distribution within that sample. So look at this graph here on the upper left. This is the same gas. This is nitrogen, and it's at 3 different temperatures. Notice that these are not just lines that look like this, right? The molecular speed in meters per second. And they're not just lines. What they are is they are lines down to 1 speed. They're curves. And what this tells us is that on average, this graph tells us 2 things. Thing one, that this curve, right, the tip of this curve, does move to the right as it gets warmer. So if you go to the bottom and you look at the graph, right, a 700-degree sample of nitrogen on average is moving like, almost like, well, probably 700, right? 700 meters per second. And on average, at 300K, right, it's moving less than 500, so 400 meters per second. And at 100K, right, it's moving at like 250 meters per second. So as you heat up a sample, it does start to move faster. But the other thing you notice is that the distribution also flattens out, right? So at a colder temperature, these are all grouped more tightly around their max. And so you'll have some moving slower, some moving faster, and then this is the average velocity. Notice that the curve widens. So as you get warmer, you have more distribution. So yes, the average molecule is moving faster. However, there is a lot less grouping around that middle point, right around that average, and you have much more variety within your sample. So yes, gases move faster as you heat them up, but they also get sort of more variation within the sample average. This right here is called the root mean square, which is referring to the fact that these are curves and not just, it's not just one average or one value. But what we find here is that the average speed, and U here refers to velocity. It's the root mean square velocity. Even though it's not a V, it still generally means the same thing, is equal to the square root of 3 times R times T divided by the molar mass of the gas. And so what this is going to tell us is, because molar mass is a denominator, that the speed, right, at which these gases are moving, the heavier they are, the lower their velocity. Looking at the picture or the graph on the right, helium, nitrogen, and chlorine as gases, right, at a given temperature. So unlike the one on the left, this one is at 1 temperature. What you'll notice here, right, is that on average, the lighter the gas at a given temperature, right, helium versus nitrogen versus chlorine, the lighter the gas, the faster they're moving, the heavier the gas, the slower they're moving. But it's also interesting to note that the heavier the gas, there's less variation around the average. The lighter the gas, yes, the average gas speed is higher, but there's also a lot more variation around that average. All right. All right. Gas diffusion. Gas diffusion is the rate at which a gas diffuses across a room. So what this represents is ammonia. This is hydrogen chloride or HCl gas. And the reason why this NH4Cl, which is the product of these two gases, so NH3 is a gas, HCl is a gas, when they collide, they make a solid, NH4Cl. I'm not sure if I did this demo for you in 10th grade. We were going to do it again this year. you get this solid, cloudy white solid happening in the air. Now, what you notice is it's closer to the HCl side. So you can conclude if it happened exactly in the middle, which one, they would be moving at the same velocity and diffusing across the room at the same speed. But because they're happening over here, closer to the HCl, you can conclude that the NH3 is a lighter gas. And that is true when you look at the molar masses, right? And so the rate or velocity of gas A relative to the velocity of gas B is equal to the square root of the molar mass of B over the molar mass of A. And so you could get this equation and derive it for yourself if you like by using this equation above. And so you would just put one on top, one on bottom, and instead of the molar mass of A and the molar mass of B, and you'd find that there would be a flip that happens here. Now, what this is also telling us is, right, A is moving faster than B, or B is moving faster than A if you have a number bigger than 0, right? Or sorry, 1. And so if you have a number bigger than 1, right, in this ratio, then A is moving that many times faster than B. If you have a decimal, that means that B is moving faster than A. And you can calculate their relative rates based on that velocity. So that wraps up this unit on gases. I'm going to have you look at some sample problems in the book and then use those to go a little deeper into some of the concepts that I just reviewed, and then to apply those in problem form. Of course, as always, send me an email if you have a specific question about what I overviewed. We can find this in Chapter 5 of your textbook, starting halfway through Section 5.4.